Okay, so I left you with the question of how far is the Sirius B from Sirius A in that sort of famous binary system. Well, I'm also trying to encourage you to keep using this expression. So L equals theta d. So L is the physical separation, where theta is the angular separation, and d is how far away the object, this system we're talking about. Okay, so we can put in the values we had. So we had 11 arc seconds. So again, convert to radians by dividing by this number, and then multiply by the distance. So it's 2.6 parsecs, and there are 3.1 to 16 meters in a parsec. So if you want to do it in meters, then you get this number here. And if we divide by 1.5 10 to 11 meters in a for an astronomical unit, we end up with 29 astronomical units. So if you want to be safe, then use SI units and convert back to AU, then that's fine for this. But I'll just let you know here that there is a much shorter way of doing this, and that is to because of the definition of the parsec that we have in workshop 2. So I noticed there were at least 60 or 70 people not attending workshop 2. A lot of good examinable material in workshop 2 for the next assessments and the final assessment. So you should be attending all the workshops, please. So if you put the physical length in AU, the angle in arc seconds, and the distance in parsecs, then everything works, because this length will be 1 AU if this is 1 arc second and this is 1 parsec. So actually, if you want the answer in AU, you just do the 11 arc seconds times the 2.6 parsecs, and you get 29 AU straight away. But just whatever you do, don't mix these two things up, or else you get in terrible trouble. So if you want to play safe, do it in SI units. If you're confident what you're doing, then you can use these units here. So the reason for converting to AU was that 29 AU is about the size of our solar system. The orbit of Neptune is sort of out here, and here we can see the sort of orbit of Sirius B. So it has about that sort of size. It's elliptical, as we'll come to later. And another wacky thing, of course, because Sirius B is a white dwarf star, it's a similar size to the Earth. It's actually quite a massive white dwarf, so it's a bit bigger than the Earth. But a lot of white dwarfs are basically exactly the same size as the Earth itself. So it's a peculiar object, and you can begin to, perhaps get a feel for how close these binary stars can be. Well, they can be a lot closer than that, of course. Okay, so let's get on to the more sort of mathematical bit. So we're going to set up the derivation of Keplers Law, but using the actual physics here, the forces and everything. So we're going to consider two stars with masses M1 and M2. We're going to make things simple by just assuming circular orbits, so that both stars are in circular orbits and that they are both orbiting the center of mass. So again, you need to sort of get clear in your head what's going on actually. And so it's not that one star is stationary in space somehow and the other one's orbiting around it. It's that both of them are orbiting around the center of mass. And we're going to take the radius of each orbit to be R1 and R2 respectively, and that the total separation between the two stars is L. And all we need here, sort of 3 bits of physics really, so Newton's laws of motion and gravity, and circular motion laws, and that's all we need. So here's a diagram just to clarify all of those variables. So here are 2 stars, M1 and M2. So masses, M1 and M2. Again, don't confuse masses with magnitudes. And here is the center of mass, okay, about which both stars are orbiting. Okay. So star 1 is doing a circle like this, going around this center of mass, not going around the center of mass. Star 2 is doing a bigger orbit, can't do it on the cursor, going around with a orbital radius of R2, and the orbital radius of star 1 is R1. And the total separation between the two stars that I'm calling A is clearly going to be just R1 plus R2. So the center of mass definitely, has to be on a line between the two stars at all times, and so they go around, sort of opposite each other. And we will also introduce the orbital speed. So this is the circular speed, if you like, that the star 1 is going around in a circle with a speed v1, and star 2 is going around in a circle with speed v2. Okay, so I've got a little movie here showing you this idea of orbital motion around a center of mass. Sort of green dot in the middle is the center of mass. Okay. The blue star is the more massive star here, and so you can see that it's closer to the center of mass than the lower mass star, which is whizzing around the outside. But at all times, the center of mass is on a straight line between the stars. Okay, and you can see that obviously both stars have the same period. Okay, but just that the lower mass star with the bigger radius orbit also goes around faster. Okay. So that's the picture to keep in mind. Okay, so let's apply some, just some basic physics. Hopefully you've all come across circular motion before, but if not, everything is here. So circular motion is what we'll do first. So in order to get something to move around in a circle with a speed v and a radius r and a mass m, then you need to, apply a force in order to keep it moving around in that circle. Okay. And that's just given by this formula here. So mv squared over r. Okay. So we can apply that to star 1. Okay. And so this is just true of any circular motion. It doesn't matter what the force is that's causing it to move around in a circle. Okay. Could be a mass whizzing around on a string, in which case this would be the tension. Obviously here it's the force of gravity, but we'll come to that in a moment. Okay. So another simple relationship for circular motion is relating the speed and the radius and the period. So I'm going to call it period P here. You may have called it capital T before, but I'm going to call it capital P. And so obviously the circular velocity is just the distance traveled to go around one orbit divided by the time it takes to go around one orbit, which is the period. So that's 2 pi r over P. And so we can substitute for V1 in here, okay, to give us this expression here. And then star 2 is also doing circular motion, so we can do exactly the same thing for star 2. Okay. So as I said, P is the period, and it's the same for both stars. Okay, so that's the circular motion part. Next, we need to bring in the center of mass. So you saw the center of mass in action earlier on the animation. Okay, so again, center of mass we can easily find from this kind of relationship when you've just got two bodies. The center of mass of a two-body system will be given by this, where R1 and R2 are the distances from the center of mass that we defined in the diagram before. And you probably recognize this kind of formula because it's basically just like a pivot or a moment or a couple. All of those different terms, they all come down to the same thing. Okay, so basically, as we saw in the animation, the higher mass star is going to be nearer the center of mass and the lower mass one is going to be further away. Okay. And so this distance R1 is related to this distance R2 by the mass ratio of the system. So finally, let's bring in gravity. Okay. So the force, F1, that is causing star 1 to move around in a circle, has the same magnitude as force 2, which is keeping star 2 moving around in its circle, and it's just given by Newton's law of gravity. which is just g m1 m2 over the separation squared. Okay, so this is important. Okay, and common mistakes by students who are getting A, R1, and R2 mixed up. Okay, so A is the total separation between the two objects, which is equal to R1 plus R2. Okay, okay, so let's complete this by combining all of this together. So obviously we had the circular motion equation for the force, and now we've just had the gravity expression for the force, so we can equate those because they're the same thing. It doesn't matter if you do it for star 1 or star 2. And you can see that we can eliminate M1 here. Okay, so that just tidies that up a little bit. I've made the period the subject here. But at the moment, we've got kind of a mixture of A and R1 here. So in order to sort of get us back to sort of Kepler's original third law, we're going to eliminate R1 in terms of A. So we can do that by going back to the relationship between A and R1 and R2, and then bringing in the center of mass. We hadn't used the center of mass here yet, so we can bring in the center of mass equation. So R2 is just M1 over M2 times R1. So then we can take a common factor of R1 out, okay, over here. And so what we're going to do now is make R1 the subject of this and substitute it back into here. So R1 is going to be A times M2 over the sum of the masses. Okay, so you can see what's going to happen here. So we end up with A cubed on the top, okay, and the sum of the masses here on the bottom. Okay. So this is showing us now that p squared is proportional to A cubed. So some of you may recognize that as Kepler's third law. Okay. And but obviously here we're more interested in measuring the masses of stars. So I'm turning the formula around here to give us M1 plus M2, which is the sum of the masses of the two stars, in terms of things that we might be able to observe. So as we just did that example for the Sirius system, then we can measure the separation between the two stars if we can see them. And if we wait long enough and watch them go around each other, then we can measure P, the period. Okay, so this is starting to show us that if we measure the parameters of the binary system, it's going to start telling us something about the masses of the stars. Okay, so this equation here is a key one for this part of the course. So this is what I would refer to as Newton's form of Kepler's third law. Okay. So Kepler only told us that p squared was proportional to A cubed. Newton came along with his law of gravity, so big G coming in here, and basically worked out the constant of proportionality. Okay. So now that you've got that sort of more quantitative version of Kepler's third law, why don't you just have a go at using it to confirm what the mass of the sun is? Obviously, you know the answer, but put in the properties for the Earth. So you've got A being 1 AU and P being 1 year, but obviously putting everything into SI units just to confirm that things come out as they should. So you can see Kepler's law, Newton's form of Kepler's third law in action. I should say law there. Okay, so if you have a go at that, and we'll carry on after the break.